When we fit a multiple regression model, there are a lot of assumptions that we make, and also once we fit an actual multiple regression model to a real life data, there are different parts of the output that we get from any software that we use to fit. In this module, we have discussed all the outputs that we get when we use R to fit a multiple regression model. When there are several explanatory variables and there is one variable that depends on it, so we have several estimates of the regression coefficients. But although we have a number of explanatory variables, sometimes not all of them are statistically significant in our study. We will see in this module how we can test the overall fit of a multiple regression equation, and also how each of these variables, explanatory ones taken at one time, can be tested as statistically significant or not. In the previous module, we had discussed the multiple regression and the fitting of a multiple regression to a numerical problem. The problem that we had looked at had, to begin with, two dependent variables y1 and y2, where y1 was the measure of success in grad school and y2 was the score on a major review paper. And there were four explanatory variables x1, x2, x3 and x4, where x1 was a measure of intellectual ability, x2 was measure of work ethic, x3 was the second measure of intellectual ability, and x4 was a measure of spatial ability. We had seen, after constructing the matrix of correlation coefficient, that x1, x2, x3 or x4, none of them positively or significantly influenced the second dependent variable y2. So we had carried on the study with one dependent variable y1, and we had retained the two explanatory variables which were highly correlated with y. So as a continuation of this previous As a continuation of the fitting of the multiple regression model, in this module we will discuss the Anova table, which is also a part of the R output when we fit a multiple regression model to the data. So let us begin with the Anova table of fitting a regression model with two explanatory variables x1 and x2. So as you can see, the Anova table output when both x1 and x2 are entered in the first block when predicting y1 appears as follows in R. We have the sum of squares available for the regression model, the residual as well as the total sum of squares. We have their corresponding degrees of freedom. For regression, we have degrees of freedom 2 because we had two explanatory variables, and the mean squares are also available. Using the mean square for regression and residual, they have calculated the f-test statistic value. Using this f-test statistic value, we can test the significance of the model, and we also have the corresponding p-values. Since we can see that the significance level is less than alpha, in this case assumed to be 0.05, the model with variables x1 and x2 are statistically significant in predicting y1. The sum of squares for the residual is given by 727.929, which is sum of the squared residuals, and the mean square residual is 42.78, which we obtained by dividing 727.29 by the degrees of freedom 17. The total sum of square is 11,420.95. This is the sum of square differences between the observed values of y and the mean of y. The regression sum of square, which is 10693.66, is the sum of square differences between the model where yi hat equals beta naught and yi hat equals beta 0 plus beta 1 x1 plus beta 2 x2. The regression sum of square is also the difference between the total sum of squares and the residual sum of squares. So if the reader is interested, they can try subtracting 727.293 from the total sum of square, which is 11,420.95, and can see that we get the result, which is the regression sum of square. And the regression mean square is given by 5346.83, which is computed by dividing the regression sum of square by its degrees of freedom, which is 2. In this case, the regression mean square is based on 2 degrees of freedom because 2 additional parameters beta 1 and beta 2 were computed. Now let us look at the changes that occur in regression coefficients. When more independent variables or independent terms are added to a regression model, the regression coefficient changes as a function of the relationship between both the independent variables and the dependent variables. Let us illustrate that using the example data that we have used. So a minimal model can be written as yi hat equals beta naught, which is predicting y1 from the mean of y1 results in the following. So yi hat equals beta naught, which is equals 169.45, where 169.45 is the regression estimate for this model. A partial model predicting y1 from x1 results in the following model. Now in the following model we have only used one explanatory variable, that is x1. So yi hat equals beta naught plus beta 1 x1. And after we fit this regression model, the estimates of the coefficients are got, and in terms of the estimates of these regression coefficient, we can write the above expression as yi hat equals 122.835 plus 1.258 times x1. A second partial model predicting y1 from x2 is given by the following expression: yi hat equals beta naught plus beta 2 x2I. Again, using the estimates of beta 0 and beta 2, we can write the prediction model as y hat I equals 130.425 plus 1.341 x2. As we have established earlier, a full regression model which is predicting the value of y using both the explanatory variables x1 and x2 is written as yi hat equals beta naught plus beta 1 x1 plus beta 2 x2. Yi hat can now be written in terms of the estimates of beta naught, beta 1 and beta 2 as follows: yi hat equals 101.222 plus 1 times x1 plus 1.071 times x2. If the reader recalls, this is the exact prediction model that we had come up with in the previous module when we had discussed the fitting of a multiple regression to this data set using the two explanatory variables x1 and x2. So as we can observe, the values of both beta 1 and beta 2 change when both x1 and x2 are included in the regression model. In the previous few slides, we have first seen the simplistic case where y is estimated by the mean value of the observed values of the dependent variable y, which was yi hat equals beta naught. In the second case, we had only used x1 as the predictor variable, and we have seen that the values of beta naught and beta 1, or the estimates of beta naught and beta 1, had changed. Again, in the next model, when we had only included x2, we had a different set of estimates for beta naught and beta 2. And finally, in the full regression model, when we had both the predictor variables included, we have seen that the estimates of the beta 0, beta 1 and beta 2 had changed again. Now, there is also a change in R square, or the coefficient of determination, that happens by changing the set of explanatory variables that are included in a multiple regression model. As I have pointed out before, when we observe R square and we wish to decide on whether the model is a good fit or not, then by the inclusion of every new explanatory variable, there is an improvement in the value of R square. However, we want to keep a check on the number of explanatory variables that we include in our model, because increasing the number of explanatory variables will invariably increase the value of R square. We cannot use R square as a measure of goodness of the number of explanatory variables in the model. So instead, what we use is adjusted R square. The adjusted R square adjusts for the number of observations as well as the number of parameters that we are estimating in our model. So if after correction for the number of parameters or the number of variables included, the increase in the value of R square is not significant, then we decide on not including the new variables in the model and making it more complicated. So the unadjusted R square value will increase with the addition of terms to the regression model. Now the amount of change in R square is a measure of the increase in predictive power of a particular dependent variable or variables, given the dependent variable is already in the model. Let's look at, for example, the effect of work ethic, which is x2, on success in graduate school, which is our dependent variable y1. If we look at the effect of work ethic on success in grad school, and if we could assess it, given one already has a measure of intellectual ability x1, then the following table represents the results that we get. So when there are no variables included in the model, that is a simplistic model where yi hat equals beta naught, then R square is 0 and there is no increase in R square. Again, if there is only x1 in the variable in the equation, then the R square is 0.584 and the increase is 0.584 because previously R square was 0. Again, if both variables x1 and x2 are included in the regression equation, then we see that R square has now become 0.936 and the increase in R square from before is 0.352. And a similar table can be constructed to evaluate the increase in predictive power of x3 given x1 is already in the model, where x3 was our third explanatory variable. Now if we look at the next table, which is similar to the one before, we see that although both x2 and x3 individually correlate significantly with y1, x2 contributes a fairly large increase in predictive power in combination with x1, while x3 does not, because the increase in R square after we include x3 when x1 is already in the model is simply 0.008, and in case of x2 it was 0.352, which was substantially larger than 0.008. Now because x1 and x3 are highly correlated with each other, knowledge of one necessarily implies knowledge of the other. So in regression analysis terms, x2 is a combination, in combination with x1 predicts unique variance in y1, while x3 in combination with x1 predicts a shared variance. So it is possible to do significance testing to determine whether the addition of another dependent variable to the regression model significantly increases the value of R square. This significance test is the topic of the next section. Now, in order to test the significance of an explanatory variable in a model, we use the sequential significance testing. In order to test whether a variable adds significant predictive power to a regression model, it is necessary to construct the regression model in stages or in blocks. This is accomplished by entering the independent variables in different blocks or sequentially one after the other. For example, if the increase in predictive power of x2 after x1 has been entered in the model was desired, then x1 would be entered first and then we would enter x2 after x1 is already present in the model. Then x1 would be entered in the first block and x2 in the second block. When we provide R with the independent variables to fit into a multiple regression model, by default R sequentially adds each independent variable to the model, testing at each stage whether the inclusion of the variable in the model was statistically significant or not. In other words, when we provide R with a list of explanatory variables, what R does is it starts with the simplest model where no explanatory variables are added, and then internally it takes one explanatory variable at a time and adds it to the model to check whether it is significant to stay in the model or not. If it is statistically significant, it retains that in the model and adds the second explanatory variable. If not, it does not retain it and moves on to the next one. Now there are various relationships between variables in a multiple regression. Because we are dealing with a number of explanatory variables here, there are different dimensions to the relationship between variables which are present. So when we have several independent variables, then a variety of relationships can be defined between the dependent variable and the independent variables, and between the independent variable and the dependent variables as well. So let us explore some of these relationships in our example data. So let us look at the variables which are unrelated. So the unrelated independent variables in this example are both x1 and x2, which are correlated with y. However, x1 and x2 are uncorrelated with each other. In the example, we can see that x1 and x2 are correlated with y1 with values 0.764 and 0.769, which can be considered very high positive values of the correlation coefficient. The independent variables x1 and x2 are correlated with the value of 0.255, which is not exactly 0 but which is close enough to 0, and thus it attributes its value to a low relationship or a weak relationship between x1 and x2. And if the reader wants to consult the values of the correlation coefficient between the pairs of variables in this study, they can refer to the module which we have previously discussed. Now in this case, when we discuss that x1 and x2 are not correlated strongly, however, they both are independently strongly correlated with y, then they contribute independently to predict the variability in y. It doesn't matter which variable is entered into the regression equation first and which is entered second. Now the following table of R-square change predicts y1 with x1 entered first into the model and then x2 entered as the second explanatory variable. So we can see that the R-square was 0.764 when we had entered x1 into the model, and it then became 0.968 when both x1 and x2 were present. And the next table of change in R-square predicts y1 with x2 entered as the first variable and then x1 and x2 both entered into the model. The value of change in R-square, as can be seen from the table, from x1 of model 1 in the first case is 0.584 and to model 2 in the second case is 0.345, which is not identical but close enough. Now had the correlation coefficient between x1 and x2 been 0 in place of 0.255, the change in R-square values in the two above tables would have been identical. Now let us look at the related independent variables. In case of x1 and x2, both of them were correlated with y and they were x1 and x2 are correlated to each other. In the example data, x1 and x3 are correlated with y1 with values of 0.764 and 0.687 respectively. So each of them by themselves, x1 and x3, are strongly correlated with y1. And between themselves, the independent variable x1 and x2 are correlated with the value of 0.940, which is an extremely high positive correlation. So under this type of relationship, there is a high chance that there is multicollinearity present, and we have already seen in some previous modules as to how we can deal with this. In the presence of multicollinearity, it becomes difficult for the multiple regression equation to differentiate the effect or the influence of one variable, one explanatory variable on the dependent variable from the influence of another explanatory variable which is highly correlated with the first one. So in this situation, it makes a great deal of difference which variable is added to the regression model first and which is added second. In the previous case, when x1 and x2 were not correlated to each other, in any order we could have added these two explanatory variables into the model. But in our current situation, since we have related independent variables, then the order of inclusion in the model affects the model a lot. So let us enter x1 first and x3 second, and this results in the following R-square change table. So if you look at the table, the R-square when x1 was only present in the model is 0.584, and when x1 as well as x3 are added into the model, it is 0.592, which is an extremely insignificant amount of rise in the value of R-square. Again, the next table of change in R-square predicts y1 with x3 first and then with both x1 and x3 present in the model. So in case of just x3 in the model, we have R-square 0.472, and in case of x1 and x3 we have 0.592. So as before, both tables end up at the same place, in this case with an R-square of 0.592. In this case, however, it makes a difference whether a variable is added to the model first or second. As we can see, variable x3, for example, if added first, has an R-square change of 0.561. And if added second after x1, it has an R-square change of 0.008. So in the first case, it is statistically significant, while in the second it is not. So as the two independent variables become more correlated, the estimates of the regression coefficients become unstable. This we have seen in the study of multicollinearity in detail in some previous modules. Now let us look at the last type of variables or the last type of relationship that we can see between variables in a multiple regression model. They are called suppressor variables. One of the many varieties of relationship is when neither x1 nor x2 individually correlate with y, but x1 is correlated with x2 and x1 and x2 together correlate highly with y. In our example data, this phenomena can be observed in the relationships of y2, x1 and x4. In the example data, neither x1 nor x4 is highly correlated with y2, with correlation coefficient of 0.251 and 0.018 respectively. Now the variables x1 and x4 are correlated with a value of 0.847, which is a quite high positive correlation. Now fitting x1 followed by x4 results in the following table. So when we fit the first model, which only has x1, we have an r square of 0.063, which is a very insignificant amount of r square. But in the second model, when we fit using both x1 and x4, we see that there is a significant increase in the value of r square. So it has now changed from 0.063 to 0.301. So here we have also presented the table with the estimates of the coefficients for the first model where only x1 is present, and we can see that the estimate of beta naught is 114.938 in the first case, and the estimate of beta 1, which is the coefficient corresponding to x1, is 0.150. And we can also see that at a level of significance 0.05%, x1 is insignificant in this model. However, we can see that in the second model, when we first enter x1 and then we include x4 as well as the second explanatory variable, then at a level of significance 0.05, we can see both x1 as well as x2 are significant in this model. In this case, the regression coefficients of both x1 and x4 are statistically significant when entered together, but insignificant when entered individually. It is noted that the regression coefficient for x1 is positive and the regression weight for x4 is negative, which means that x1 positively influences y. So as the value of x1 increases, the value of y increases as well, and the coefficient corresponding to x4 is negative 0.783, which is a high negative correlation. So as the value of x4 increases, there is a decrease in the value of the dependent variable y. In this case, the variance of x1 that does not account for variance or in y2 is cancelled or suppressed by knowledge of x4. So the variable x4 is called a suppressor variable. So in this module, we have seen how we can use R to fit a multiple regression model. We have seen what the codes are that are required to fit a multiple regression model to a data set, and we have also looked at the different features of R which helps us perform the different statistical hypothesis testing which are related to fitting of a multiple regression model.